Hi all, and welcome to the sixth lecture of the deep learning course. Today we're going to be discussing about recurrent neural networks, which together with convolutional neural networks are one of the most important families or pillars of network architectures. So today we're going to try to see what is special about recurrent neural networks and how we can use them in everyday practice. So specifically today we're going to start with exploring what makes sequences special. So recurrent neural networks are specialized neural networks for sequences, and we will see why do we want a special architecture for them. We're going to then discuss how the backpropagation is adapted to be able to train recurrent neural networks. We're going to study LSTMs, which are advanced versions of recurrent neural networks, as well as some variants. We're going to continue with discussing attention in neural networks, as well as transformers, which are a class of sequence models that are very popular lately. And then we're going to discuss various applications of sequence models. To start with, so that we understand better what is so special about sequences, let's see what kind of sequences we have around us in everyday life. So first of all, we've got videos, right? Like videos are basically sequences of frames, and videos is probably the biggest of, some of the biggest data that we have nowadays. It's in everybody's phones. Stock exchange creates data sequence, right? Like the ticks over time are creating time series that are amenable to, representation learning. Biological measurements come in sequences, so you can measure at each time of the day your heart rate, your blood pressure, and the likes, and then you would have a sequence of biological measurements. Climate measurements can come in sequences, so you can have like videos, for instance, of icebergs moving, or of temperatures, and of other weather measurements. Market analysis, for instance, what's going on with regards purchase and sales of various economic units. Speech and music are another case of time series of sequences. User behavior in websites, computer games. Basically, the point that I'm trying to make here is that, in fact, most of the things can be assembled in sequences in reality, right? Like the fact that we don't have data in sequences is more of a choice rather than what reality dictates. So, finding models that can work with sequential data is very important. What makes sequences special? Why can't we just use regular MLPs or regular convolutional neural networks? Well, for one, a very big difference is that with sequences we've got no more IID data. We cannot assume that our data is independent. Well, by definition it's not independent because they come in a sequence, right? So everything, like every next observation depends on all previous observations, since we have a sequence of data. And the distribution changes, so they're not identically distributed. Given my past, the distribution of my future will change. If I drive very aggressively with my car, the chances that there will be an accident will be different than when I would drive more calmly. Another thing is that sequences might be of arbitrary lengths, while with images, for instance, an image will always be of a fixed dimensionality. Of course, you can have larger or smaller images, but you cannot have infinite images. And then the obvious question is, how can we model dependencies at different temporal scales, or how to make a model that works just as well for 10 seconds as for 10 minutes. With sequences, we presumably can have cycles in our computational graphs. So that's more of a technical point. However, that is another issue, and we have to figure out a way to learn with cycles. Some more theoretical or like more advanced topics that we might want to, or we might see, or you might see in the future. There is a problem of credit assignment, the so-called credit assignment. So at each time step, we have some reward, so to speak, or our prediction makes an error or not. So which of the infinite time steps in the past is responsible for that error or for that reward, and to what degree? So how do we assign credit to each of our past time steps? That's a very important question also that is not necessarily addressed. Chaotic behavior is a very interesting other problem with recurrent networks. So basically we can show that, or one can show that recurrent networks are basically resembling dynamical chaotic systems, and this means that their optimization is or can be in principle chaotic, and fixing that is a topic of major interest. What is more, we have great temporal redundancy. That is especially with when it comes to, with videos, with speech, with music, so with types of data that are very similar from one time step to the other. And one could see this redundancy as a problem, or because we have to store all this very similar information, or it could also be seen as a feature or as a property that we can somehow resemble to have better or more efficient models. This also relates to the area of slow feature learning or of spike neural networks, which is a bit more it is an old topic, but also a very futuristic one in the sense that there is no good solution nowadays still. So is temporal redundancy a curse or a blessing? That is to be seen. So sequences are actually having a lot of unique properties and peculiarities, and introducing some sort of inductive bias in our neural network design such that to account for these unique properties is quite important. So here I'm putting or I'm summarizing some of these inductive biases that we introduced to account for these issues. So for non-IID data, our solution is to come up with state models. So now we have stateful models that carry information over time, and to use the chain rule of probabilities for decomposing, the final likelihood. For the arbitrary lengths, a very frequent solution, the most popular solution, is to share weights. For the gradient assignment problem, we've got the backpropagation through time that works well when we're interested in recurring neural networks. For chaotic behaviors, we have better variants of RNNs, so LSTMs or GRUs. Although this is still a problem, it's just it's mitigated with those variants. For temporal redundancy, we've got spiking neural networks or slow feature learning, but I leave this out. It's out of the lectures, let's say, domain. It's out of scope. Regarding sequence, so let's take one by one these inductive biases regarding state models or chain chain of probabilities. So sequences are by definition non-IID. So if we have one word, one sentence, we can decompose it according to the order. So Donald, Trump given Donald, is given Donald Trump, and so on and so forth. Now the continuation, the remaining of the sentence has a likelihood which depends on the past, right? So this is what we mean by non-IID. And one way to compute how likely this, the rest of the sentence or overall the sentence is to decompose this with a chain of probabilities and then model each of the terms independently. So basically this is what recurrent neural network does when it comes to sequences. And keeping a memory state means that we want to somehow maintain the past influence for future reference. So we want to keep some sort of summary, some sort of aggregation of the past, a state, a memory, right, the representation of the past. And memory can take all sorts of forms. I mean, it can be a vector, it can be a matrix, whatever. It could be a table. Basically, any representation that maintains some connection or some summary of what has happened before. So the memory, how the memory is typically implemented. So at time step t, we want to project all previous information onto this state space st. So our state space is basically a form of memory. And then this memory can be controlled by neural network with parameters theta. So this is how we implement the memory by neural network. And then at time step t, we take this state, this memory state, and we reuse our neural network parameters and the previous state to predict the next state, and then based on the next state, maybe make a prediction for the outcome, for the output, and so forth. And since this is a recursive operation, often with some sort of Markov chain assumption, and in your state depends only on the previous time step only. So S of t, the state at time step t, depends only on t minus 1, t minus 1 depends only on t minus 2, and so forth. This is to simplify our model. To address sequence of arbitrary lengths, I mean, that's actually a very important point. The thing is that we cannot, and ideally we should not have a constraint or a very big constraint on the sequence length. The thing is that we simply cannot really decide what the length of a sequence should be. If we do so, then we introduce a bias via our model. So the model should not, in principle, have a problem with varying, unknown, or even infinite sequence lengths. So this is not a very easy problem to solve, right? Like, what about infinite sequences? That's actually a big problem. One logical solution is to reuse parameters, to share parameters through time. So this means that we don't have to learn like different parameters for every time step. We can learn them once and then reuse them. In comparison, imagine if you would have an infinite convolutional neural network, then you would have to learn infinite filters for each of the layers, right? So that's a very relevant analogy. For the same reason, we're going to have an infinite convolution and learn infinite filters. For the same reason, we also should not, or we cannot easily have infinite number of parameters for our time steps. Now, a memory, can be graphically represented with this picture. In the simplest case for recurrent neural network, as we'll see also in the following sub-lecture, it's just it comprises a neuron or a set of neurons with three types of parameters for the output, for the input, and for the memory. What the U matrix transforms the input. It embeds it it projects it to the state space. Then the matrix W takes the previous state space and projects it back again onto itself. And matrix V takes that state space and transform it to some output, some desired output. So it's our final prediction, so to speak, or it can lead to our final prediction, so to speak. The variable st, so the state variable, is our memory vector. It's our memory vector because with this we can represent what happened, what was the previous state in the past. To remove the cycles, because that's also one of the problems, we can just unfold the graph. So write down each time step explicitly, like in this picture. And in this picture, if we do it like that, there are no cycles anymore. No cycles. We've got shared parameters, but this is something that the backpropagation can deal with, as we'll see. Of course, in theory, we could have problem with infinite time steps, right? So we would have to unfold for infinite time steps, but in practice we can cut the sequence short, as we'll see. So that's called truncation, and that's not necessarily a bad design choice, because after all, more often than not, we don't really need to have infinite past. It's actually going to be irrelevant and even disturb our future predictions. Well, of course, this sounds a bit like an excuse. Ideally, we would like to be able to model everything and then focus on, have the model learn what it wants to focus on. But all I'm saying here is that truncating the sequence to a maximum length is not necessarily a bad choice. And putting all these things together, we can arrive at our first recurrent neural network, which is basically these three simple equations. Our input is transformed by a linear operation, by linear operator u, and added to a transform version of our past. And then we take this member state, so our current state of our system, and then we transform it linearly and with a softmax such that we make a prediction. And softmax here, of course, assumes a 1 out of k classification problem. So this is our recurrent neural network, as simple as that. Three equations. We could have loss terms, one loss term per time step. So for instance, for text generation, right, like we want to, each new word could produce a loss, like so predicting the next word, for instance. But we can also think of not having those. So basically churning the data sequence and making a prediction again. So for instance, is this a happy sentence, a sad sentence, or an aggressive sentence, and so on. So this doesn't really require generating losses per time step. You only need to do it once in the end. But in the general case, we could have loss terms only once per time step. Thank you.